Predicting traits from biomedical images without visible cues is a significant challenge, as algorithms are designed to capture visually correlated ground truth. This problem is particularly critical in biomedical sciences, where the solution can improve the efficacy of non-invasive methods. For instance, predicting MGMT methylation status from MRI images is crucial for treatment decisions of glioma patients. Despite numerous efforts, contemporary models exhibit suboptimal performance, and the underlying reasons for this limitation remain unclear. This study aims to demystify the complexity of MGMT status prediction by performing benchmarks of existing models, including transfer learning, and dissecting their architectures by observing gradient flow across layers. Additionally, a feature selection strategy is applied to improve model interpretability. The findings suggest that current models are unlearnable and may require new architectures to explore applications in the real world. The author's approach involves a comprehensive exploration of the MGMT status prediction challenge, highlighting the need for novel models that can effectively capture non-visible cues. The study's results underscore the urgency of addressing this issue, as using less robust models poses a significant risk in critical biomedical scenarios. Radiogenomics, a rapidly evolving field, associates imaging phenotypes with genomic characteristics, such as gene expression patterns or individual mutations. This field has been instrumental in treating complex diseases like cancer through precision medicine. However, conventional practices, including invasive tissue extraction and assays, hinder the growth of radiogenomics. Radiomics, which involves binary classification of genotypes using MRI, CT images, has shown promising results, with advanced imaging algorithms like deep convolutional networks demonstrating accuracy above 90%. Nevertheless, reproducibility across independent cohorts remains a challenge, with accuracy dropping to below 80%. In biomedical sciences, input data and corresponding labels are often gathered from separate sources, making it challenging to predict subtle signatures not prominently visible in images. To address this, we focused on predicting MGMT methylation status from 3D MRI images of glioma patients, a crucial marker for choosing chemotherapy to increase patient survivability. Glioma images exhibit subtle visible characteristics like diffusion, which could be linked to MGMT status, enabling clinicians to determine its status through non-invasive methods. Previous studies have attempted to predict MGMT status from MRI images, primarily using datasets from the Cancer Genome Atlas and in-house datasets, but have reported low accuracy. Recently, the RNSA-BRATS Challenge launched an extensive and standardized dataset, providing a public platform for radiogenomic prediction. Predicting MGMT status from MRI images remains a challenging task, despite numerous efforts to improve performance. The BRATS 2021 competition reported a cumulative AUROC of 0.6, with a ResNet model achieving the best result. However, subsequent studies have failed to exhibit optimal performance, with some even suggesting no correlation between MGMT status and MRI images. This inconsistency in results motivates a deeper investigation into the computational task of predicting phenotype from MRI images. To address this, the present study employs a process-driven approach, adopting benchmarks of existing models with transfer learning, gradient flow analysis across layers, and feature selection strategies. The BRATS 2021 Challenge dataset is utilized, consisting of 585 glioblastoma patient MRI scans, with 278 and 307 samples belonging to unmethylated and methylated MGMT, respectively. The dataset comprises 4 imaging modalities: T1 weighted precontrast, T1 weighted postcontrast, T2 weighted, and T2 fluid attenuated inversion recovery. All imaging modalities are utilized in this study, unless otherwise specified. Brain images are preprocessed by resampling and skull stripping to ensure consistency. This study aims to demystify the complexity of MGMT status prediction, identify the necessity of indigenous tools, and explore possible reasons behind the persistent saturation in performance. By employing a comprehensive approach, this research seeks to provide insights into the limitations and potential avenues for improvement in predicting MGMT status from MRI images. This study leverages a standard convolutional neural network (CNN) architecture, comprising ResNet, DenseNet, and EfficientNet, which have demonstrated robust performance in various biomedical classification tasks. The optimizers employed are ADAM and RMS-prop, with hinge and BCE logit loss serving as loss functions for classification tasks. The batch size is set to 4, with a learning rate of 0.0001, and epochs ranging from 25 to 100 in certain scenarios. Image dimensions are fixed at 256 × 256. Model performance is evaluated using accuracy, AUROC, sensitivity, and specificity. Transfer learning is also applied, capitalizing on its effectiveness in scenarios with limited data and dense architecture training. ImageNet and MedNet weights are used for model weight initialization. Two transfer approaches are employed. The first utilizes previously trained models as feature extractors, training the remaining fully connected layers. The second involves fine-tuning, where the complete architecture is trained with initial weights from MedNet. An explainable approach is adopted to enhance the predictive capability of current models. Pyradiomics is used to extract various features from MRI images, including first-order statistics, shape-based features, and gray-level CO occurrence matrix features. The Mann-Whitney U-test is conducted to determine if the distributions of these parameters significantly vary. Features with a p-value is less than or equal to 0.05 are considered statistically significant and retained for further analysis. Recursive feature elimination using a random forest algorithm is then applied to identify the most informative features. These top-ranked features are selected to construct a predictive model, whose performance is evaluated against an existing model. The application of machine learning models to predict MGMT methylation status in brain tumors using MRI images is a pivotal aspect of this research paper. To identify the most significant features from an initial set, the authors employ a recursive feature elimination algorithm. These features are then grouped based on their similarities through hierarchical clustering, guiding the development of novel architectures for the prediction task. The authors evaluate the predictive performance of three convolutional neural network (CNN) models: DenseNet 264, ResNet 101, and EfficientNet across all four MRI image types. The results indicate that the accuracy ranges between 49% and 63%, with no clear indication of a specific image modality consistently providing the highest performance. Despite employing complex architectures and extensive training, the models exhibit suboptimal predictive accuracy, highlighting the challenges in this predictive task. Given the inconsistent predictive accuracy, the authors choose ResNet for further analysis due to its smaller parameter size and lower computational requirements. This choice is crucial for downstream analysis, as it allows for more efficient processing without compromising the predictive capabilities of the model. The selection of ResNet also underscores the importance of balancing model complexity with computational efficiency in such tasks. The choice of image type is crucial for capturing tumors and their characteristics. T2 images are particularly effective for this purpose. The performance of neural networks such as ResNet, DenseNet, and EfficientNet across various image modalities is then analyzed. Five-fold testing highlights the strengths and limitations of each model. The impact of error metrics and optimizers on predictive performance is also discussed, focusing on hinge loss with RMS and ADAM, as well as BCE with RMS-prop. The challenges of training complex models on small datasets and the benefits of transfer learning are emphasized. The paper compares hyperparameters for loss functions and error metrics on training and test datasets, highlighting the overlap in accuracy for the hinge loss with RMS and ADAM. It explores transfer learning approaches, starting with interdomain transfer using ImageNet weights and intradomain transfer with MedNet weights. The ResNet 10 model was used as a feature extractor, with only the fully connected layers trained. Despite training over multiple epochs, there was no significant improvement in predictive performance, suggesting ineffective cross-task feature transfer for challenging tasks. The study then fine-tuned the ResNet architecture with pre-initialized MedNet weights on the BRATS dataset, resulting in noticeable enhancements in predictive accuracy on the training data. However, the test dataset's performance remained unchanged initially and later decreased, leaving unclear whether the model captured specific patterns. In transfer learning, the application of MedNet weights enables the adaptation of pre-trained models to new datasets. A crucial aspect of this process is training the feature extractor and fully connected layer using the current dataset. This approach allows the model to learn domain-specific features and fine-tune its performance. Evaluating the model's performance on both training and test data is essential to avoid overfitting, where the model becomes overly specialized to the training data and fails to generalize to new, unseen data. This phenomenon can be mitigated by monitoring the learning curve, which provides insights into the model's behavior and potential generalization issues. Further investigation into model behavior is necessary to ensure that the model is learning meaningful patterns rather than simply memorizing information. This includes analyzing sensitivity, specificity, and gradient flow, which provide valuable insights into the model's decision-making process. A thorough understanding of these metrics is critical to developing a robust and generalizable model. By examining the learning curve and model behavior, researchers can identify potential issues and take corrective action to improve the model's performance. This involves refining the model architecture, adjusting hyperparameters, and optimizing the training process to achieve better generalization. Ultimately, a comprehensive understanding of the model's learning process is essential for developing accurate and reliable models that can be deployed in real-world applications. The authors delve into a detailed investigation of their model's performance to understand the observed saturation and accuracy at 60%. They employ learning curves that depict the relationship between the model's performance and the number of training epochs. The analysis reveals fluctuations in sensitivity and specificity during both training and testing phases, leading to erratic behavior in the early epochs of the training dataset and throughout the test dataset. These fluctuations result in sudden spikes or drops in accuracy, as the model tends to favor one class over the other. This insight suggests that the lower observed accuracy is not due to learning behavior but rather random favor causing either lower sensitivity or specificity. To further explore the observed random favor, the authors examine the gradient flow within the model during training epochs. They present histograms of the cumulative model weight of the initial layer and its corresponding gradient for each epoch. The results show that the model weights remain relatively stable, while the gradients exhibit significant variability. This variability in gradients could be a potential source of the random favor observed in the model's predictions. This section provides valuable insights into the model's performance and highlights areas for improvement. The use of learning curves and gradient analysis offers a comprehensive understanding of the model's behavior and can guide future work on enhancing its accuracy and stability. Gradient flow analysis reveals that ResNet's primary layer weights remain largely unchanged during training, indicating ineffective learning from the training data. This phenomenon is most pronounced in the initial layer, responsible for capturing major imaging features. Furthermore, certain model layers fail to receive new gradients during backpropagation, resulting in minimal weight updates. To investigate this, the study explores the relationship between model complexity and performance by adding convolution layers to ResNet. However, the results show no clear correlation between model complexity and performance metrics such as accuracy and area under the receiver operating characteristic curve, AUROC. This suggests that simpler architectures can also achieve comparable performance. These findings imply that the model's inability to effectively learn from the training data is not solely due to its architectural complexity. Rather, it may be attributed to the ineffective optimization of model weights, particularly in the primary layer. This highlights the importance of weight optimization techniques in deep neural networks, particularly in the initial layers responsible for feature extraction. The relationship between model complexity and predictive performance is investigated in terms of accuracy and area under the receiver operating characteristic curve, AUROC, across various convolutional neural network (CNN) architectures. Despite their capabilities, these models struggled to capture subtle patterns in images, highlighting the need for domain-driven knowledge to enhance the current paradigm. One potential solution lies in extracting explainable radiomic features, which provide insights into image characteristics and help understand model weaknesses and potential avenues for improvement. A comprehensive analysis of radiomics features across four modalities: FLAIR, T1, T1CE, and T2 reveals significant features unique to each modality. Notably, the FLAIR modality yields the highest number of significant features. To optimize feature selection, recursive elimination is employed to choose the best features for each image. This approach demonstrates that each image requires distinct features to achieve maximum performance. The results show that FLAIR, T1, T1CE, and T2 select 6, 23, 8, and 1 features, respectively, with FLAIR providing the highest performance using 6 features. These findings underscore the importance of modality-specific feature extraction and selection for enhancing predictive performance in CNN architectures. The section focuses on identifying key radiomic features that differentiate between MGMT methylated and non-methylated categories. Figure 5a highlights statistically significant features across various image modalities, with T1, T1CE, and FLAIR sharing common features. However, T2 has a unique feature not found in other modalities. Figure 5b illustrates the overlap of these features among the modalities. A feature ranking using recursive feature elimination with a random forest is presented in Figure 5c, emphasizing the importance of certain features. Lastly, Figure 5d displays a dendrogram showing 3 clusters, each containing 2 features, demonstrating the clustering of similar features. This analysis aims to pinpoint the most relevant radiomic features for distinguishing between MGMT methylated and non-methylated categories. The importance of feature selection in predictive models is particularly highlighted in the context of predicting MGMT methylation status from MRI images. The authors compare the performance of their model using all 43 features and only the top essential features identified through a feature selection process. The results demonstrate that feature selection improves model performance, although the metrics are still lower than desired, indicating that these features alone may not be sufficient for real-world applications. The authors also explore the association between the top features by creating a dendrogram, which reveals 3 clusters with 2 features each. This clustering could be used to derive custom feature maps that enhance the learning of convolutional networks. However, caution is advised to avoid biases and ensure generalization across diverse datasets. The study emphasizes the need for indigenous tools in this domain, as current techniques are often not designed to solve problems involving non-visible cues and images. It highlights the challenges encountered during the training process, including poor learnability of the models, and suggests further exploration is necessary to develop more effective solutions. In medical imaging, relying solely on visual patterns can lead to inaccuracies in recognizing subtle minor variances. To address this limitation, the authors draw on the concept of aggregating multiple weak learners to form a strong learner, as established in the literature. This approach provides insights into avenues for enhancing model architectures and is explainable, allowing for the identification of influential radiomic features that can improve performance. However, incorporating these features may introduce bias, necessitating further exploration. The current study highlights the sensitivity of the problem, rather than providing a concrete solution, and offers a direction towards a solution. Future research aims to develop custom feature maps informed by extracted knowledge of essential features, addressing underlying issues. This approach is supported by previous studies, such as Katya Pinker et al.'s work on radiogenomics, which demonstrated the potential applications of radiogenomics in medical imaging. The authors also reference studies on precision medicine for acute myeloid leukemia, such as Hartmut Donner et al.'s review, and research on predicting IDH status through MRI features, as presented by Haishya Dane et al. Additionally, they cite Jing Yan et al.'s study on predicting 1p19q codeletion status from magnetic resonance imaging using deep learning in adult-type diffuse lower-grade gliomas. By acknowledging the limitations of visual patterns and exploring the potential of radiomic features, the authors contribute to the development of more accurate and explainable models in medical imaging. This approach is grounded in the understanding that machine learning models can learn from weak learners to form a strong learner, and that incorporating domain knowledge can enhance model performance. The application of artificial intelligence in personalized healthcare has seen significant advancements, particularly through the use of magnetic resonance imaging, MRI, for non-invasive evaluations. Various studies have leveraged MRI radiomics and machine learning to predict biological characteristics, such as tumor mutation status, in rectal cancer, perihilar cholangiocarcinoma, and gliomas. In gliomas, researchers have developed signatures for predicting IDH mutation and 1p19q codeletion status. These studies utilize advanced techniques like convolutional neural networks and deep learning to analyze MRI data, demonstrating the potential of AI in enhancing diagnostic accuracy and personalized treatment strategies in healthcare. The development of genotype prediction of ATRX mutation in lower-grade gliomas further highlights the role of AI in improving healthcare outcomes. These findings underscore the importance of integrating AI into healthcare systems to provide more accurate diagnoses and targeted treatments. By leveraging MRI radiomics and machine learning algorithms, researchers can better understand the complex biological characteristics of various cancers, ultimately leading to improved patient outcomes and survival rates. The research applies machine learning techniques to medical fields, focusing on cancer and glioma diagnosis and prediction. It utilizes MRI-based deep learning radiomics for identifying HER2-low positive status in breast cancer and predicting disease-free survival. Additionally, it discusses improving hypertrophic cardiomyopathy mutation prediction using cardiac cine images and predicting H3K27M mutations in brainstem gliomas with conventional MRI and clinical features. The studies also explore the role of machine learning in identifying H3K27M mutations in midline gliomas through multiparametric magnetic resonance imaging radiomics and predicting response to radiotherapy and prognosis in glioblastoma, demonstrating the potential of machine learning in enhancing diagnostic accuracy and improving patient outcomes. The prediction of MGMT promoter methylation status in brain tumors using radiogenomic classification has been a topic of significant research. Studies have utilized multiomics fused feature spaces, attentive multimodal CNNs, and vision graph neural networks to predict this status from MRI scans. These methods leverage different modalities of MRI, such as T1, T2, and diffusion-weighted imaging, to improve accuracy. Synthesis-based imaging differentiation representation learning enhances the quality and relevance of imaging data used for classification. Promising results have been demonstrated by several studies, including those by Kahira et al., Das, Qureshi et al., Muhammad et al., Kolias et al., and Hu et al. These advancements have the potential to provide a less invasive diagnosis for brain tumors, eliminating the need for surgical biopsy. Research studies have explored the potential of radiomics and deep learning models in predicting the methylation status of the MGMT promoter in glioblastoma using MRI scans. These approaches leverage the power of medical imaging to non-invasively diagnose this aggressive brain cancer. One approach, employed by 27, combines radiomics with latent space shape features to improve predictive accuracy. Alternatively, 28 and 30 rely on deep learning models to analyze MRI scans and predict MGMT promoter methylation. Separate studies, 29 and 31, have validated the use of MRI-based models for predicting MGMT promoter methylation in gliomas, a broader category of brain tumors that includes glioblastoma. Furthermore, 32 and 33 provide comprehensive evaluations of MRI-based deep learning tools for detecting MGMT promoter methylation, highlighting the clinical potential of these approaches. These studies collectively contribute to the development of non-invasive diagnostic tools for glioblastoma, enabling clinicians to identify patients who may benefit from targeted therapies. By harnessing the capabilities of radiomics and deep learning, researchers are moving closer to creating accurate, efficient, and patient-friendly diagnostic methods for this devastating disease. Deep residual learning has revolutionized image recognition, offering unparalleled efficiency and accuracy. This approach, pioneered by He et al., involves stacking residual blocks to ease the training process and improve performance. Densely connected convolutional networks, another breakthrough, enable the learning of complex representations by connecting every layer to each other. Efficient Net, a novel model, rethinks model scaling for convolutional neural networks, achieving state-of-the-art results through a combination of compound scaling and neural architecture search. Transfer learning has emerged as a crucial aspect of deep learning, allowing pre-trained models to be fine-tuned for new tasks. This approach leverages the knowledge learned from large datasets like ImageNet, a comprehensive hierarchical image database for training and testing. The survey on transfer learning highlights its significance in reducing the need for massive datasets and computational resources. In the realm of medical image analysis, MED3D has been proposed for 3D medical image analysis, enabling the extraction of valuable insights from complex medical data. Computational radiomics, another area of focus, aims to decode the radiographic phenotype by identifying patterns and correlations in medical images. These advances have far-reaching implications for disease diagnosis, treatment, and patient care. The authors cite recent research papers that leverage transfer learning to improve classification accuracy in speech disorder diagnosis, image superresolution, and object detection tasks. Orozco-Arellava's work demonstrates the effectiveness of transfer learning in classifying patients with different speech disorders across various languages, achieving improved accuracy. Jin et al. Propose a deep CNN-based approach for fast and accurate image superresolution, incorporating skip connections and network-in-network (NIN) architectures. This methodology enables the model to capture both local and global features, leading to enhanced performance. Wang et al. Tackle multi-class 3D object detection within volumetric 3D computed tomography, QUART, baggage security screening imagery, utilizing a 3D object detection framework to achieve improved detection accuracy and efficiency. Feng et al. Employ an adaptive boosting approach for machine learning-based compressive strength prediction of concrete, integrating multiple weak models to achieve enhanced predictive performance. These works collectively highlight the versatility and effectiveness of transfer learning and deep learning techniques in addressing diverse applications.